CERN in Geneva, the largest physics lab in the world, they've just built a special scientific instrument to study neutrinos. It's called CNGS, CERN Neutrinos to Gran Sasso, and it's a beam of neutrinos starting off right under my feet, directed to the Gran Sasso labs in central Italy. CERN just switched on a neutrino beam aimed through the Earth to the INFN Gran Sasso laboratory, some 730 kilometers away from Geneva. This is the latest addition to a global endeavor to understand these most elusive of particles and unlock the secrets it carries about the origins and evolution of our universe. Neutrinos are continuously produced in the Sun and stars, and they are the most abundant matter particles in the universe. Some 60 billion neutrinos pass through a space the size of a fingertip every second, yet their mass is so small and they interact so weakly that they are very hard to study. Today we know there are three families of neutrinos: electron, muon and tau neutrinos, and that they oscillate between one family and another. This process is only possible if neutrinos have mass, but this has not been measured yet. The beam leaving CERN consists entirely of muon-type neutrinos. By the time it reaches Gran Sasso, some will have oscillated into tau-type neutrinos. Neutrino oscillation happens over a very large distance, which is why the experiments designed to study the oscillation are placed 730 kilometers far from the beam source at CERN.
We are inside a tunnel connected to the 400 billion electron volt accelerator at CERN in Geneva, and right here are generated the neutrinos that the Italian laboratory of Gran Sasso will use to study the oscillations between the second and third family. Since the accelerator is built on a horizontal plane, the first thing to do is to deflect the protons traveling inside these red objects. These are electromagnets used to deflect protons in the direction of Gran Sasso. Because the Earth is round, they must be deflected in the vertical plane as well. These protons will so travel inside these deflecting magnets behind me, and after a while they will hit the target, a graphite cylinder with which they interact. During these interactions, the protons produce mesons, which are relatively light and unstable particles, charged positively or negatively. When these mesons decay, they produce neutrinos. We are interested only in the neutrinos produced by the positively charged mesons. So behind the targets, we have two magnetic lenses, called horn and reflector, that squeeze the positive mesons in a parallel beam. This beam is then sent inside a 1 kilometer long vacuum tunnel, called the decay tunnel, where the mesons decay and produce the neutrinos we need. The neutrinos then cross the Earth and re-emerge at Gran Sasso, where they find detectors capable of measuring the neutrino oscillation.
And this is where the neutrino beam from CERN gets to, right here, in the heart of the Gran Sasso National Laboratories, the largest center in the world for underground physics. This is the underground area of the Gran Sasso Laboratories hosting the OPERA experiment. Yves de Clé is the spokesperson of the international collaboration that runs this very large experiment. Yves, how will OPERA see neutrinos and their passage?
I will now show you how the detector will register the neutrino interactions in the lead it is made of, and how we will later analyze events to identify the nature of the neutrino that interacted. On this very light mechanical structure, we will install special bricks made of 50 sheets of lead and 50 sheets of emulsion, a special substance similar to photographic film that can record in a very precise way the passage of the particles coming from the interaction of a neutrino with a brick. We have 30 tons of bricks and a total of 12 million sheets of emulsion to record the interaction. The whole point will be to determine in which brick the interaction took place, and to do this, we put layers of detectors called scintillators in between each layer of brick. These scintillators record the passage of particles in real time. Knowing the time correspondence between the passage of particles and the time of departure of the beam from CERN, we can make the difference between the interaction generated by the beam and the interaction from the background noise due to cosmic rays, that are anyway very weak in this underground camera. The difficulty of this experiment will be to determine which interaction is the one identifying the tau neutrino. Here is one of the 200,000 elements of the opera target, one of the 200,000 bricks that will be put inside the detector by a robot. Each of them weighs 8 kilograms, so the total weight of the bricks inside opera will be 1,800 tons.
And I am honored to place the first of the 206,000 bricks of opera. The effect that Gran Sasso experiments are looking for is extremely subtle. Of the many billions of muon neutrinos leaving CERN, just about 15 of those that oscillate will be detected over the 5-year lifetime of the experiments. This will, however, be enough for scientists to complete another part of the neutrino puzzle.
Esistono neutrini da varie sorgenti.
Neutrinos come from different sources, and we try to analyze and understand them. Neutrinos are emitted by collapsing stars or by the sun. These are astrophysical or cosmic neutrinos. Others originate in the atmosphere through the impact of primary particles, essentially protons, with layers of the atmosphere itself. Finally, neutrinos can also originate from radioactivity inside the Earth. Of course, in the next few years, attention is going to be focused on artificially made neutrinos. The neutrino beam from CERN is a titanic enterprise.
Is where we have just produced a neutrino beam for the Gran Sasso.
So we're extremely happy with what happened. After many years of simulation, theoretical work, fabrication, installation, finally we were able to send our proton beam down to the line, hit the target and create our neutrinos. So this is extremely positive, and for us, accelerator physicists that have been working for years on this project, it's really, really very exciting. Right after the first injection in the proton beam line, we had the beam going right in the center of the target. So this was, you can imagine, a very big relief.
I'm very excited because it's the very first time that I join in a startup of these dimensions. And it also was very satisfying up to now, but I think that's the reason is that it has been very well organized and planned already. It's also stressful because, of course, the time is very limited for all these preparations. What I did up to now until the commissioning was mainly to set up all the instrumentation, to do the follow-up of the design and installation of it. And then I'm also the liaison physicist between the accelerator and the experiments, so which means I'm the link person between the people at Gran Sasso, the opera people, and here at CERN.
It's difficult and it's not, because we have done this type of neutrino beams over the years in different versions here at CERN and elsewhere. It's more difficult this time because we try to produce a neutrino beam which is a lot more intense than previously, and therefore every single component is being pushed more to its limits than we did in the past. So what really happens in the control room is, in this place, in this round of the control room, first of all, the colleagues operate the SPS accelerator. So they let the protons come into the accelerator, accelerate them up to maximum energy, and then with a little magnetic kick send them out into a transfer line. In this proton transfer line, we observe the protons traveling towards the target. We steer the protons slightly, we correct, if you wish, the way they travel, so that we are sure that we hit the target as well as possible in the center. We also, from here, switch on the magnetic lenses which come after the target, and we observe the products of the decay of the pions. We observe the muons in our muon detectors. All of it is done from here.
It's very important that the proton beam hits really the center of the target in a very precise way, and we allow the center of gravity of the proton beam batch to only move by a few tenths of a millimeter in the center of the target. The target is a graphite rod which is extremely small. Its diameter is 4 to 5 millimeters. So you can imagine now that we have to steer, meaning to put the proton beam very, very finely onto this spot.
For the first time at CERN, we will send a particle beam in another country, and the particle beam is not staying at CERN. So the distance from CERN to Gran Sasso laboratory is 732 kilometers, and the main challenge is that we have to ensure the accuracy of the beam direction from CERN to Gran Sasso laboratory. For this, we will use different kind of techniques, and the first of these techniques is the GPS measurement, which has been realized on this kind of geodetic monument that you can see here. So now the starting point, which is at CERN, and the ending point, which is at Gran Sasso, in the same coordinate system, we can easily determine the two directions of the beam, which is the slope direction and the azimuthal direction. And the physicists are able now to determine the theoretical position of all the components of the Gran Sasso line. So you know that the Earth is not a plane, but it's a sphere, more or less, and we need to be sure that we know quite accurately the differences between the plane and the geoid reference system, as we called it, in order to locate very accurately all the magnets on the accelerator beam line. And we use also something which is special and very interesting. This is a gyroscope. Let's say that we can measure an orientation, a direction between 2 points with respect to the north, geographical north. And this is very important because using this technique we do not propagate any error. So make a cross check at the end of the CNGS line, and the accuracy was very good. And we finally expect that we can achieve the accuracy of 17 meters at the level of the Gran Sasso lab.
Of all the known particles, neutrinos are the most mysterious, and one of the most important milestones for contemporary physics is to verify experimentally that the oscillation of muon neutrinos to tau neutrinos is the one that has been discovered in atmospheric neutrino observations. The CNGS project will answer this question, and with other neutrino experiments around the world will contribute to understanding the crucial role of neutrinos in the formation of the universe we live in.